In this video, we're going to look at numerical methods. Most of the equations that you've come across in the past have been relatively easy to solve. Let's take a quadratic equation, for example. If we had x squared is equal to 49, we would look to solve the equation by square rooting both sides. So we'd end up with x is equal to plus or minus 7. If we couldn't take the square root of both sides, we might look to try and solve the equation by factoring. If we couldn't factor, we could choose between the quadratic equation or completing the square. Many equations that appear in the real world aren't as easy to deal with and often don't lead to exact solutions. An example might be cos x is equal to x. We could find a numerical solution to this equation. The level of accuracy can be really quite high and it depends on the technique that you use. In this video, we're going to look at a range of different techniques to find numerical solutions to equations. So let's take that equation now, cos x is equal to x. So we've got now cos x is equal to x. So you could look now at a range of the techniques that you know to solve this, but ultimately we would need to use a numerical method. So let's look at one particular approach that we could do. We could now draw two different graphs. And I'm going to define now the f of x to be equal to cos x. So I'm setting the left hand side now equal to some function of x, which I'm going to call f of x, and the right hand side of the equation equal to a different function of x, now which we're going to say g of x is equal to x. All I'm going to draw is y is equal to the f of x and y is equal to the g of x. So let's look now, and we'll take this and we'll start now from negative pi by 2. So here's negative pi by 2. We'll come round, pi by 2 is here. We'll come round down to pi, and then we'll come back up like so. So that now is y is equal to cos x, or if you like, y is equal to the f of x. And then if we went the other side, it looks something like that. So that's a rough sketch. So let's put this on. Y is equal to cos x. We've got this point right here, which is going to be pi by 2, comma 0, or if you like, pi by 2 is about 1.57. So let's just put approximately, that's approximately 1.57. We've got now 0, comma 1, we've got minus pi by 2, comma 0. So this is y is equal to cos x. Let's now draw y is equal to x. Y is equal to x looks something like that. So we've got now a straight line through the origin, and we can label this up now, y is equal to x. So using a graphical method, we can show that for these two particular functions of x, there's going to be one solution, and it's going to be about there. So if I look at this by eye, I can see now it's going to be approximately, let's say 0.8, 0.7 or 0.8. So on the x-axis here, we could say now that x is going to be approximately 0.7 to 0.8. Clearly, if I use a graphical calculator or a computer, I would get a much better level of accuracy. In an exam, you wouldn't be expected to say, well, it is now going to be 0.72 or 0.81. What we'd be expected to do is show by using two different graphs that the root, and generally we call the root alpha, the root alpha is going to be between 0.5 and 1. So you might be asked to show that that's the case. So we know that this is about 1.57. We know that this is 0. So we'd be expected to show that there's a root somewhere in this interval. And that root is generally called alpha. An alternative here would be to now graph y is equal to cos x minus x. So if we graphed y is equal to cos x minus x, we could look to see, and let's say that this is going to be the function h of x. What we'd do is look to see where h of x was equal to 0. This is less intuitive though, as you don't know what that graph is going to look like. You might do, but it's less likely. So just having a rough idea of what it would look like, it will probably look something like so. So what we would do now, here is the x-axis, we would look now for the solution where it crosses now the x-axis, where h of x is equal to 0, and we would look for a solution. And again, if you're using a graphing calculator or computer, then that would be another approach. This is easier as we can just express this now as two functions of x and go ahead and draw each, and look at the point of intersection. The alternative is to graph y is equal to cos x minus x now and look where it's equal to 0. This now leads us on to a second approach that we could use to approximate a root. So if we can now express the equation as y as a function of x and ensure that the graph is continuous in the interval that we're interested in, we can evaluate a point either side of where we believe to be a root and show that there's a change of sign. So if we look at this one right here, there's a change of sign. To the left of this root, let's say that alpha here, let's say that alpha is going to be approximately, let's say 0.7. So if we tested a point here, and let's say that this point was going to be 0.6, and then we tested a point just here, 0.8, if when we evaluated 0.6, we got a positive answer, and we evaluated 0.8 and got a negative answer, we could say that there was a change of sign in a continuous interval. Therefore, there's a root alpha somewhere between these two. Now, this method has its limitations, and we'll look at those shortly, but this is one way that you could show that there's a root in this interval from 0.6 to 0.8. So let's go ahead and do that. Let's take a graph that we might know. Let's say we've got the f of x. So let's say the f of x is going to be equal to, let's take x squared minus x minus 6. So if I drew this now, we could go ahead, let's just factor it first. Let's say the f of x. This is going to give me now x minus 3, and then we'll have x plus 2. So we'll just sketch this up now. So let's go ahead and do that. So here's our graph. We're going to have a point of intersection now on the x-axis. That's going to be minus 2 just here, and then we're going to have positive 3. So here's a parabola, something like so. So we'll come down to the minimum point and then back up. So a rough sketch right here, and we could say that y is equal to the f of x. So we know that there's a root just here, and that's going to be 3, 0. As we can solve this, we can set this equal to 0, and then we've got one just here at minus 2, 0. So let's say I took some value just here. So what we'll do is take a value here, and often you'll see this being called x sub 1, and then we'll take one value, x sub 2, to the right of this root. Now, the closer you get to the root, the better. What I'm going to do here is evaluate the f of 2.5 and then the f of 3.5. When we look at some equations, we'll have now a closer approximation or a closer value that we're going to take that's going to, let's say, 2.9 and 3.1. What I'm looking to do now is show that there's a change of sign in this continuous interval. And when I'm talking about a continuous interval, there's no break in this graph. So for example, the graph of y is equal to 1 over x is discontinuous, as we've got now a gap. This one, you can see in the interval that I'm considering, there's no gaps. So let's go ahead and evaluate this right now. So if I took a calculator and put in now the 2.5, so let's put in now the 2.5. So we would put this in. So what we have now is our answer. Let's do our answer minus 3 multiplied by our answer plus 2. So if I do that, I'm going to end up now with minus 2.25. So this is now minus, and we'll put this in, minus 2.25. Now this is a negative value. So let's go ahead now and do 3.5. So let's do 3.5. And then I'm going to have now my answer. And I suppose I could do this without using a calculator. Just to save me time, I'm just going to put it through here. And we are now going to get 11 over 4, which is 2.75. So let's put this in. So what we could say then is 2.75. And we would finalise this by saying there's a change of sign in a continuous interval. Therefore, the root alpha lies between 2.5 and 3.5. So let's put this here. We've got alpha is going to be between 2.5 and 3.5. So this is the second method. Before, we were looking at two functions of x. We were setting them now and having one here, cos x, and now showing that there's some root just here. This method is now looking at where the f of x in this particular case is going to be equal to 0. So this is where it's going to be crossing the x-axis, and if we can show that there's a change of sign in that continuous interval, then there's going to be a root alpha between the value of x sub 1 and the value of x sub 2. Okay, let's just take some time to think about some of the issues with this particular method. Let's say I had now a cubic equation. Let's say the f of x, so we'll have the f of x, and I'll factor this. Let's take some linear factors. Let's say we got 2x minus 1, and then we've got now x minus 1, and let's say we've got 2x minus 3. So if I wanted to see where the f of x was equal to 0, so let's go ahead and do the f of x is equal to 0. I'm going to draw a quick sketch. So with my quick sketch, I'm going to have something. We're going to now be going through at -3, so go through the y-axis at -3. We're going to have now a solution at 1/2. We will have one at 1, and then we'll have one at 1.5. So our cubic equation is going to look something. Let's draw this. Give or take, so we'll come through, we'll come up, we'll turn round, it will turn back round, we'll come through, turn round, and then come through this way. So now let's just put this on. Y is equal to the f of x. So we've got now a root just here at 1/2, that's this factor right here. We've got one at +1, which is just there, and then one at 3/2. So what I've got here now are 3 points of intersection. So there are going to be 3 solutions. If I considered now x sub 1, let's take x sub 1 to be equal now to 0. And if I took, let's say, x sub 2, these are the points I'm going to evaluate, to be 2. Now, I'm going to pick a point just here, and this is going to be, and let's just put this on. If I pick this point here of 0 now, so I've chosen 0, there's 0, and there is 2. If I evaluate this right here, we can see the following. Let's just, in fact, let's just make, let's just take, in fact, they'll be perfectly fine. Let's go ahead and do that. So if I take now 0, this point right here, what I've got is the point here. So the 0 is going to give me now a negative value. So if I put 0 through here, I get now -6. If I put 2 through here, consider where 2 is. 2 is going to be positive. Now, this is telling me that there's a change of sign in this continuous interval, which is clearly true, but I've now got these 3 different roots. So one particular drawback of this method now is that I'm evaluating these 2, and these aren't massively different in terms of their numeric value from 0 to 2, but I've actually now got 3 different roots in that interval. So that's one drawback. Now, if I did as well, let's say I did the f of 1/4 and the f of, let's say, now 5/4. If I did, let's just put this here, let's say I had now x sub 1 is equal to 1/4, and then x sub 2 is going to be equal to 5/4. So these are the 2 points that I'm going to be testing. Now on here, so the last time I saw that I had 3 roots in this interval when I took now these points right here. Now what I'm going to do is take the point here, which is going to be 1/4, and then I'm going to take the next one, which is going to be 5/4. So 5/4 is going to be just here. So we can see that this will give me a negative value, and this will give me a negative value. But we've got 2 roots in this interval. And the same, if I took a point now somewhere else, we could see now if I took a point just here, it's positive here and it's positive here. So when we're using this method, we need to be very careful in terms of what we're choosing for our values of x sub 1 and x sub 2. As we can end up now evaluating and having roots in here, we can have multiple roots, yet we don't know that. And in the same way, we could end up now with these 2 negative signs, yet there be 2 roots in this particular interval. So often it's a case now of getting a very close approximation to the root such that we don't miss solutions or end up having a number of solutions in that interval. Let's take another example of where this might cause us some problems. What I'm going to do is say now that the f of x, so let's say the f of x is equal to, and we'll go for the quantity x minus 5 all squared. So if we look at this, we've seen this graph before, y is equal to x minus 5 all squared. That's just a quadratic equation, and we've shifted it now 5 places to the right. So our parabola now will touch the x-axis, and it will do something like so. So we got the axis of symmetry, x is going to be equal to 5, and then it will do something like that. Okay, so this is a point now 5. If we evaluated the f of, let's go now, the f of 4, and then we took the f of 6. So I'm saying now that I'm taking my value here to be x sub 1, that's going to be 4, and then x sub 2 to be equal to 6. We're going to have a positive result here and a positive result here. Now, I could even go to the f of 4.9 and the f of 5.1, which is a fairly tight interval just here. That's picking this point here and this point here. I'm still going to end up with a positive value and a positive value, which would suggest now that there's no root, as there's no change of sign, despite this being continuous. And if we look at it, we know there's a root. We've seen this time and time again before, but it's not actually crossing through the x-axis, it's simply touching it. So this is another drawback of the change of sign in the continuous interval. So just be aware of one of the limitations here. So we've looked now, when we have an example, this is just a cubic that we've seen before, now where it's suggesting we don't have roots, or we don't realise how many roots we've got, and also where we're not crossing the x-axis. So if we look now, the f of x is equal to 0, so we can see the f of x is equal to 0 now when x is going to be equal to 5. But this method doesn't show that. Now, we could look at an alternative way of doing this. So if we looked at this now, let's say we had the f of x and we expanded this out. Let's say the f of x was equal now to x squared, and then we had minus 10x plus 25. Now, if we split this up and we wrote the f of x is equal to 0, and we did some rearranging, we could say that x squared would be equal now to 10x minus 25. So this goes back to the first example I looked at of cos x being equal to x. We could say now that this would be a function of x, and this would be a different function of x. And we could go ahead and graph those. Now, if we did this, what we'd end up having is something that looks like this right here. So we would have now our quadratic, and then we would have a curve. So our quadratic would look something like so down here. And then we would have now one point where the graph and the line, or the two graphs just touch, and that point now would be just here. And that's not a massively accurate drawing, but hopefully it'll give you some idea. So what we've got then, we've got this point just here, and we can see clearly x is going to be equal to 5 at this point here. So this method, it is not always massively handy, especially if we're just touching the x-axis. So what I've done here is split it up and drawn x squared. This is the function x, f of x, so y is equal to the f of x. And this one now is y is equal to the g of x. So let's put this here, g of x. So g of x is 10x minus 25, which is a straight line, and then the f of x is x squared, which is a parabola. And we know that satisfies the equation. 25, so we got now 25, and then is equal to 50 minus 25. So we got that point of intersection where x is going to be equal to 5. So that's a different way of looking at it. With all of these examples, I'm using very basic functions so you can get some idea of what's going on here. Okay, let's look now at a function. Let's go ahead and look, let's say y, so we've got now, let's say the f of x. So the f of x is equal to 1 over x, and we know for this particular function, the domain x belongs to the reals, and we can't have x equal to 0 now. We can't divide by 0. So this is just the reciprocal function. Y is equal to 1 over x. So we've seen this graph many times before. This is discontinuous, okay, so let's look at this. So it would come up something like that, and it'll look like that, and then we will take now the other side. So we've got now y is equal to the f of x. It's just 1 over x. If I took a point just here, let's say I took, again, the interval, I'm not going to make the interval particularly tight here. Let's say we took x sub 1. and then we took x sub 2 to be just here. Let's put x sub 2. So let's say we had now here, let's go for minus 1. So we've got now x sub 1 is equal to minus 1, and then we took x sub 2 to be equal now to, let's go for this point right here, which is going to be 1. So if we now do the f of minus 1, that's going to give us minus 1. If we do the f of positive 1, so this is x sub 1, this is x sub 2, we're going to end up with 1. Now, there's a change of sign, but quite clearly there's no root. We're not crossing now the x-axis. The general method that we say is there's a change of sign in a continuous interval. This is discontinuous. We can see that there's a gap here. It's not defined now for x is equal to 0. Therefore, the change of sign method is no good if now our graph is discontinuous in the interval that we're evaluating. So there are two particular methods now that we could look to find numerical solutions to the equations. We can show that there's a root in a given interval, and we can also look now at a graphical method, as we've seen here, by setting two functions of x equal to each other and then going ahead now and looking at an approximate solution. In the next video, we're going to look at a different type of different method of solving these equations called iteration, when we look at the function as a sequence with a limit. And I'm going to come back to this, but hopefully now that's given you a couple of different ways to now locate roots in a given interval. So it's either the graphical method where you're getting now two functions of x equal to each other, or you're expressing this as y as equal to the f of x, setting it to 0 and showing that there's a change of sign in a continuous interval. So let's just finish with one more. Let's show now for, and we will just take, let's say we've got now the f of x, let's say the f of x is equal to, and we will say now, let's go for x squared, and then we'll have plus x minus 12. And we want to now show that there's a root in the interval from 3 to 5. So what we can do, let's show now, and you might be asked to show that alpha, the root lies somewhere in the interval from 3 to 5. I mean, this it would be highly unlikely that you'd be asked to do this, as it's a fairly straightforward equation to deal with. So let's go ahead and do that. Let's do the following. In fact, let's just change the interval on this. Let's make it even to make this work quite nicely. Let's go ahead and do 2 to 5. Let's make this slightly more straightforward. So if I go and factor this, let's say the f of x is going to be, what we're going to have, we're going to have x plus 4, and then we're going to have now x minus 3. So here's our quadratic. We're going to have a solution just here at positive 3, and then we're going to have one at negative 4. So let's graph that. It will look something like that. Okay, so we've got this point now 3, and we've got this point which is going to be now minus 4. So x sub 1, we're going to take it just here, x sub 1, that's going to be equal to 2. We've got now x sub 2, that's going to be equal to 5. So we'll show the f of 2, and then we'll take now the f of 5. What we want to do is show that there's a change of sign in a continuous interval, and we will write that as our answer, and then that will now give us a root. So if we consider now, let's just sub 2 in, so that's going to give me, subbing 2 in, we're going to have 6, and then we're going to have now 2 minus 3, which is minus 1, so that's going to give me minus 6, which is a negative number. If we put in 5, we're going to end up with 9 multiplied by 2, just subbing it into these right here, and that's going to give me 18, which is positive. And we would now say change, so change of sign in continuous interval, so we can say in continuous interval, therefore now alpha, the root alpha, is going to be somewhere now between 2 and 5. And again, we will look at much higher levels of accuracy. That's really quite a standard example off the top of my head to show you how this method works. So we got the f of x is equal to 0, we set it now to 0, and we're considering where it's crossing the x-axis.